How can simple folding transform a 2D sheet into a compelling 3D light modulator? Dynamically adjusting the structure can shield or bounce light. The purpose of this study is to explore how kinetically adjustable surface structures can create beautiful sunshading screens that modulate heat gain and light levels in response to changing seasons. This study started with a slit and folded opening that bounced light as its diagonal folds were compressed into a pocket. We created variations of this flower petal-like pocket, studying the effects of curved folds and aggregation patterns on light and shadow effects. After testing a variety of prototypes, we settled on an accordion pleat pattern that provided the best possibilities for a room-sized kinetic modular system while still maintaining an interesting visual pattern. After selecting our test pattern, a daylighting model was built in order to test the screen's thermal and visual performance in a south-facing classroom. Our model is based on room 451 of the White Stag Block, a University of Oregon satellite building in Portland. To test the differences between the screen when compressed versus when taut, two screens were created using identical geometric cutouts. The screen when compressed is designed to allow in more light, while the stretched screen is designed to block sunlight. We used the angles of a heliodon to test the screen's shading effects at hourly intervals during the 3 seasons: the summer solstice, the fall-spring equinox, and the winter solstice. The following videos show that the shadow patterns change in a dramatic way with sun movement, particularly when the sun is low. The compressed screen blocks direct summer sun, reducing heat gain and glare. During the equinox, the screen blocks direct sunlight, allowing ample daylight into the front of the space, yet reducing heat gain and glare. During the winter, ample daylight is allowed into the space, creating a visually striking pattern in the walls and floor. The tension screen blocks even more of the direct summer sun, while still allowing diffuse sunlight into the space. During the equinox, the tension screen blocks direct sunlight. The space is diffusely lit, yet the light is never directly on any work surface. During the winter, ample daylight is allowed into the room, but not as much as with the compressed screen. The visual pattern in the space is not as striking. Because Portland's winter skies are rarely sunny, additional testing was done under an artificial sky that simulates the diffuse light distribution of an overcast day. Light sensors allowed us to compare daylight factors for the two configurations and see the light fall off with the depth of the room. Under overcast conditions, both screens block more than half the incoming light. When blocking slightly more light, the screen in tension diffuses it more evenly, reduces contrast more effectively, and creates a more visually pleasing pattern than the compressed screen. Ultimately, the adjustable screen is much more likely to be used in the spring and fall due to the variable sunlight in the seasons. In the winter, the screen is likely to be removed in order to maximize light and heat gain. As currently envisioned, screens of this type offer an exciting possibility for efficient and visually pleasing light modulation that fits the needs of various end users. We are interested in how the aperture shape, fold pattern, and mounting system can make it easy to adjust the screen for different facade orientations and functional requirements. Additional geometric optimization is necessary to bounce sunlight deeper into the space for better daylight distribution. In addition to their use as sunshades, the folded surfaces could act as aesthetically pleasing room dividers and be armatures for interactively responsive installations.